In this video, we are going to use sum and difference formulas involving inverse trigonometric functions. So we're going to find the exact value of each expression. So we have the sine of cosine inverse of 1/2 plus the sine inverse of 3/5. So both these do represent angles. So if I think of this cosine inverse of 1/2 as my alpha, and my sine inverse of 3/5 as my beta, I can think of this expression as sine of alpha plus beta. In this way, I can use the sum formula for sine to get sine of alpha, cosine of beta, plus cosine of alpha, sine of beta. Put that in green. So I need to figure out what sine of alpha is and cosine of beta, because right now I can tell that cosine of alpha is equal to 1/2 and sine of beta is equal to 3/5. So I just need to figure out what the other trig functions would be equal to. Now, one thing to keep in mind is, since this is cosine inverse, that alpha should be between 0 and pi, since that's the range of cosine inverse, and beta for sine inverse should be in between pi over 2, negative pi over 2, and pi over 2. It's one thing to keep in mind. So this being said, when I go to find sine of alpha, this is the first and second quadrant, so I know I should get a positive value for sine of alpha. And for cosine of beta, since beta is in the first or the fourth quadrant, I know cosine is always positive. So now we can actually use the Pythagorean identity to figure out what sine of alpha is equal to rather quickly, since I can say that sine of alpha is just equal to the square root of 1 minus cosine squared of alpha. That just comes from the Pythagorean identity. So I can figure that sine of alpha is equal to the square root of 1 minus 1/2 squared, which is 1/4, and sine of alpha be equal to the square root of 3/4, which means sine of alpha is equal to the square root of 3 over 2. And I can do something else very similar to find cosine of beta using the Pythagorean identity, because that would just be 1 minus sine squared of beta. So I can say that cosine of beta is equal to the square root of 1 minus 3/5 squared, which would be 9/25. Subtracting, I get cosine of beta is equal to the square root of 16/25, which, when I take the square root of the numerator and the denominator, cosine of beta is equal to 4/5. Now, using all of this information, I can plug it into this formula I've already set up. Sine of alpha is equal to the square root of 3 over 2. Cosine of beta is equal to 4/5, plus cosine of alpha, which is 1/2, times sine of beta, which is 3/5, giving me 4 square roots of 3 over 10 plus 3 over 10, which I can combine to be 3 plus 4 square roots of 3 all over 10. That wasn't so bad. So let's try it again for tangent over here. Again, I can think of pi over 4 as my alpha, and my cosine inverse of 3/5 as my beta. Meaning this can be rewritten as tangent of alpha minus beta. And the difference formula for tangent is tangent of alpha minus tangent of beta all over 1 plus tangent of alpha times tangent of beta. So I already know what alpha is pi over 4. So if I wanted to figure out what tangent of pi over 4 is, I just use my unit circle, and that's equal to 1. But for beta, I know that cosine of beta is equal to 3/5. And again, beta is going to be in either the first or second quadrants. But even more specifically, since I know cosine is positive, it's going to be actually in the first quadrant, meaning tangent should also be positive. So if I draw a triangle with my angle beta, cosine is adjacent over hypotenuse, I can use the Pythagorean theorem. To find my missing side. And I can find that that side is equal to 4. So tangent of beta is equal to 4 over 3. So using all of this knowledge, I can go back to my formula. Tangent of alpha just being 1, since I'm just using tangent of pi over 4. So 1 minus 4/3 all over 1 plus 1 times 4/3, which will be negative 1/3 over 7/3, which is just equal to negative 1/7 whenever I cancel out my 3's. Now, let's say we want to rewrite an expression in terms of u and v, just given any value for the inside of those trig functions. That can sometimes be helpful for figuring this out. So in order to do so, I'm going to have to do the same setup. So sine inverse of u is equal to alpha, and cosine inverse of v is equal to beta. And so this just becomes, using that same sine of alpha plus beta, becomes sine of alpha cosine of beta plus cosine of alpha sine of beta. And we just have to figure out what those missing pieces are. So far, I know that u is equal to sine of alpha, given that alpha is between negative pi over 2 and pi over 2, which also means that u, just going off the maximum and minimum of sine, is between negative 1 and 1. And these are those restrictions it's asking us to give. So that's one restriction. Now if I wanted to find cosine of alpha, I can use that same formula over here from the Pythagorean identity of being 1 minus sine squared of alpha. So cosine of alpha is just equal to the 1 minus u squared, according to that. And again, over here, I can tell that v is equal to cosine of beta, for beta being between 0 and pi. And again, cosine's maximum minimum is 1 and negative 1, so v has to be between negative 1 and 1. And I know that sine of beta, using that formula I wrote down on the right, is equal to 1 minus cosine squared of beta. From the Pythagorean identity, I can say that sine of beta is equal to the square root of 1 minus v squared. So now that I know all these values, I can go back and write sine of alpha just to be u, cosine of beta just to be v, so u times v, plus cosine of alpha is the square root of 1 minus u squared times the square root of 1 minus v squared. And that would be the expression with the restrictions on u and v being that they have to be between -1 and 1. Now let's try this again, but now let's involve tangents. So again, I have cosine of alpha plus beta. So I can use the identity of cosine of alpha plus beta. That's some formula to be cosine of alpha, cosine of beta, minus sine alpha, sine beta. So now I can say here that u is equal to tangent of alpha, which means that alpha must be between -pi/2 and pi/2. Which also tells me that cosine will always be positive in that area. So if I'm doing cosine of alpha, it should always be a positive value. While sine of alpha can be positive or negative. But my restrictions on u, there aren't any. It can be anything from -infinity to positive infinity. But I do need to keep in mind that cosine of alpha should always be positive. Because now I'm going to draw a right triangle to figure this out. Again, tangent being like u over 1. For alpha here, I have opposite over adjacent, and the hypotenuse will be a squared plus b squared equals c squared, so u squared plus 1. I'm going to add them together. So I can see that sine of alpha, which could be negative, is going to be equal to u over the square root of u squared plus 1. While cosine of alpha, which needs to always be positive, is 1 over the square root of u squared plus 1. Which should always be positive since I can't get any negative values from that square root. And again, I know that v should be equal to tangent of beta. And that beta is between -pi/2 and pi/2, which means that cosine of beta should always be positive. And there are no restrictions on v. It could be any value I want it to be, since tangent can achieve any value in its range. When I draw my triangle here, I'm going to get a very similar setup. My angle beta here. Again, opposite over adjacent, so v is opposite, adjacent's 1, and my hypotenuse will be v squared plus square root of v squared plus 1. So I have sine of beta is equal to v over the square root of v squared plus 1. And cosine of beta is going to be equal to adjacent over hypotenuse, so 1 over the square root of v squared plus 1. So now when I go to plug these in, I'll have cosine of alpha, which is just 1 over the square root of u squared plus 1, times 1 over the square root of v squared plus 1 for cosine of beta, minus sine of alpha, which is u over the square root of u squared plus 1, times v over the square root of v squared plus 1. They both of these terms have a common denominator of the square root of u squared plus 1 times the square root of v squared plus 1. And then their numerators would be 1 times 1, which is 1, minus u times v, which is uv. So I get this expression. But there are no limitations to what u and v can be, since they're just being squared in this square root. It'll remain positive, and I can plug in any value for each of them and help me evaluate this expression for any given value of u and v. And that is how you use sum and difference formulas involving inverse trigonometric functions.